Today we're going to be discussing two different things that sound really similar, but they're completely different. And average value and mean value theorem, they sound the same, right? Because from what we know, average and mean are the same thing, like adding up a bunch of numbers and dividing by the number of items. But in the case of calculus, they are two totally different things. So what is average value? So average value is finding the average y value of a function over an interval a to b. Okay, finding the average y value of a function over an interval. So for example, if I have a, b, and I have, let's say f of x goes from like here to here, okay? Then my average y value, so we'll say this is f of x. My average y value would be something in between 0 and whatever that number is. So let's say that number is 10, right? Then my average y value is somewhere between 0 and 10. Now, is it 5? No, because if you look at your y values, we shoot up to numbers above 5 pretty quickly, and we spend most of the function above 5. So my average value is going to be somewhere like here, maybe. My average value might be like this. Okay. And I believe you already did the exploration for this, but basically what you're looking for is that the area under whatever your average value is, that area should be the same as the area under f of x, like the total area under f of x, okay? So an average value is just the average y coordinate, like the average, like if you were to add up all of the y coordinates of all of the points in between A and B, add up all of those y coordinates and then divide, you would get this average value. So to find the average value, it's the integral from A to B of f of x dx. So that adds up all of the area. And then you need to divide by the total width. Okay, so again, average in this case is like adding up all the y values and then dividing by the widths. And adding up all of the y values is basically finding the area under the curve. So if you find the area under the curve and then you divide it by the width, that's going to give you that average y value. So for example, let's say I was given like v of t is equal to something. I'm given v of velocity. Average value would find the average velocity. So given v of t, this formula would give me average velocity, okay? Because I'm given the velocity function, this would give me average velocity. It would not give me average distance. It would not give me average acceleration. I am given the function velocity, so this finds average velocity, okay? Now, mean value theorem is a totally different thing. Mean value theorem is talking about the slope. The mean value theorem says this. It says average rate of change, aka slope, is equal to actual rate of change somewhere. I'm kind of writing this in layman's terms. I will formalize this here in a second. Equals actual rate of change somewhere on the interval. So now we're talking about slope. Okay, this is talking about slope. So let's look at what this looks like. Got A, got B, got a function f of x. Okay, so let's say I am finding the average rate of change. So you know that means the slope of the secant, right? So this is slope of secant. Okay, so the slope of the secant from A to B, connect those 2 points, create a straight line. Sorry, it's really hard to write with this pen. That's why my handwriting is always terrible. Okay, well, Pretend like that's a straight line. Okay, so I've got the slope of the secant. Can I add a straight line? Oh, I can't add a straight line. Let's do that. Nope. Okay, doesn't matter. Okay, so I have the slope of the secant between A and B. Okay, the slope of that is equal to the actual slope somewhere. And by actual, I mean instantaneous, right? Instantaneous rate of change. So instantaneous rate of change. So we're going to kind of eyeball it. Looks like to be like right about here, the slope is parallel. And then like right about like here, maybe the slope is parallel. Oh, maybe not there. Maybe like right here, the slope is parallel. So the average slope between 2 points is equal to the actual, the instantaneous rate of change at some point, at least one point. In this case, I kind of found 2 places where my slope of the tangent line is parallel to my slope of the secant. Okay, so average rate of change is slope of the secant. Actual rate of change is slope of the tangent. So what we're saying is that the secant line and the tangent line are parallel somewhere, okay, over a given interval. So the mean value theorem is f prime of c is equal to, so this is the actual rate of change, okay, that's the instantaneous rate of change, f prime of c is equal to the slope between 2 points. On a, I should say, well, I'll say this, on A to B, and actually where C is on the interval A to B. So C is somewhere in between A and B. If and only if and only if, IFF, if and only if f of x is continuous on AB. So if f of x is continuous on that interval, then the average slope between 2 points, the slope of the secant, is equal to the actual slope, the instantaneous rate of change, the slope of the tangent, somewhere over that interval. Okay, instantaneous rate of change equals actual rate of change. So again, I just introduced 2 very important topics. They sound similar because they both kind of contain the word average and mean, average value, mean value, but they're totally different things. Average value doesn't talk about slope at all. There's no slope here. It finds the average y value. The mean value theorem is about slope. So average value, not about slope. Mean value theorem is about slope. And mean value theorem isn't just a formula like average value is. Mean value theorem is a theorem. It says if a function is continuous, then the average slope equals the actual slope somewhere. So two different big ideas here. And then we're going to go through 3 examples. Okay, so for this example, we're going to find the values of C that satisfy the mean value theorem. So we see the words mean value theorem. So mean value theorem means average slope equals actual slope somewhere. Average slope equals actual slope somewhere. So what you want to do is find the average slope. So the average slope would be f of 1 minus f of negative 3 over 1 minus negative 3. So if I plug in 1, I get negative 2 minus 4 plus 4. If I plug in negative 3, I get negative 2 times 9 plus 12 plus 4. And then 1 minus negative 3, 1 plus 3 is 4. So I get negative 2 minus negative 18 plus 16 is negative 2 over 4. So I get negative 2 plus 2, which is 0. Okay? So I found that the slope between negative 3 and 1 is 0. So let's go ahead and find the actual slope. So this is the average slope. Average slope equals actual slope somewhere. So what is the actual slope? Well, let's find the slope function. Negative 4x minus 4. All right, then I get 0. And by the way, this is just a coincidence it's 0. It's not always going to be critical points that you end up finding. Add 4 to both sides. Divide by negative 4. I get x is equal to negative 1. So this is the value such that the average slope over this interval is equal to the actual slope. So what I just figured out is I have some sort of quadratic. Looks something like this. Who cares? And at negative 3 and 1, we had the same y coordinate. So like, let's say this is negative 3 and this is 1. So I have these y coordinates. Between those 2 points, I ended up with a slope of 0 because they had the same y coordinate. Okay. What I have just found is that there is a slope of 0 at negative 1. Okay. So the average slope between 2 points is equal to the actual slope somewhere in between those 2 points. So that's the mean value theorem. Okay. All right, now for these two, I have to decide whether I'm finding the average value or if I'm finding the average rate of change. So average value means average y value. Average rate of change means the average slope. So r of t is equal to 3 times 1.7 to the t represents the rate at which fish grow in a pond after 2010. Find the average rate of change between 2010 and 2020. Then calculate at what time the rate of change of the population was equal to the average rate of change. Okay, so this is the average rate of change. But am I finding the average rate of change of this function? In other words, am I finding the average value of r of t, or am I finding the average value of r prime of t? So this one is tricky because it has the words rate of change in there. But r of t is already the rate. R of t is the rate. So to find the average rate, I am going to use the formula 1 over b minus a times the interval from a to b of r of t dt. Okay, so let me walk you through this one more time because these are confusing. We are given the rate function. We are finding the average rate of change. If you're given the rate function and you're finding the average of rate, that's going to be the average y value of the rate function. I'm not going to find the derivative. If I found r prime, that's the rate of the rate. That's the derivative of rate, which I'm not asking about here. I'm asking for the average rate. So I am finding the average value of a rate of change function. Okay, so before you solve this problem, you might need to pause the video and read the problem through one more time. Make sure you really understand why I'm saying that it's using this formula and I'm not finding r prime. R is rate. We are finding average rate. So that's going to be the average value formula. Okay. So we're saying between 2010 and 2020, t years after 2010. So that's going to be 1 over 2020 minus 2010 is 10 years. It's going to be the integral from 0 to 10 of r of t dt. So we're going to find the average rate of change, and then we're going to calculate the time at which the rate of change is equal to the average rate of change. Okay, so we're going to use a calculator for this one. So first thing we want to do is figure out what the integral from 1 over 10 of 0 to 10 r of t dt is. 3 times 1.7 to the t. Function 3 times 1.7 to the, we're just going to use x here. Okay, there's my function. So I'm going to do 1 over 10. 1 over 10 times the integral from 0 to 10 of my function dx. Okay. All right, so my average rate of change is 113.412. And the context was the rate at which fish grow, or fish grow in a pond. So it's population. So that means on average, 113 fish are added to the pond each year. And again, this was because I was given a rate of change function. I'm finding the average rate of change. Okay. All right. Now, it also said find when the average rate of change equals the actual rate of change. So to figure that out, I'm going to go ahead and store this answer in alpha A. Okay, so right now A is stored as my function, as a variable, sorry. So make sure that you know how to store things. And I'm going to figure out when the average is equal to the actual. So I'm going to graph y equals A, so it's going to be a line, and then my rate of change function. And I'm going to go ahead and graph this. Okay, let's look at our window. We're going from 0 to 10. Our y min is 0. We're probably going to have to go higher than 10 since we have 113 as our average. So let's go to 200, and let's go ahead and scale by tens. Okay, change your window so it makes sense, right? All right, there we go. I can see the point of intersection. So when does the average equal the actual? 5, enter, guess. That's close enough. All right, and their point of intersection was at t equals 6.8455. 6.8455. The average rate of change was 113.412. Again, not the rate of change of the function that I'm given. The function I was given was rate of change. So the average was 113.412. That's a rate, and it's fish per year. And then when was the average equal to the actual? At t equals 6.8455. You can round that to 6.846 if you'd like. Make sure you always have at least 3 decimal place accuracy years. And that was, so somewhere in 2016, close to 2017, the rate of change was 113.412 fish per year. Okay. All right, number 11, average value or average rate of change. So we're given S of t, which represents distance a bird is from its nest in feet. Calculate when the bird is flying at its average velocity. Okay, so in this case, I'm given distance and I'm finding velocity. I am not given velocity finding velocity. I'm given distance finding velocity. So that's average rate of change. So I am going to go ahead and, sorry, I'm ignoring that phone call. I'm going to find the average rate of change. So the average rate of change would be S of 10 minus S of 0, slope of the secant, over 10 minus 0. And that's going to be 1,000 minus 800 plus 10 minus 0, 0, 0, so 0 over 10. So that's going to be 200 plus 10, so 210 over 10 is 21. So the average velocity is 21, and we are in feet per minute. So that is my average velocity, okay? And we are finding when is the bird flying at its average velocity? Okay, I shouldn't have actually circled that. I'm not done with the problem. When is the bird flying? When? That means you have to solve for t. When is the bird flying at its average velocity? So let's find the actual velocity. Actually, instead of s prime of t, let's just call that v of t. The velocity is equal to 3t squared minus 16t plus 1. So when is the velocity equal to 21? So 0 equals 3t squared minus 16t minus 20. Now, I already subtracted 21 from both sides, so I don't need to set one of my equations equal to 21. I am going to go ahead and just graph 3x squared minus 16x minus 20, and I'm going to set it equal to 0. So I'm going to have to change my window settings. It's somewhere between 0 and 10, still reasonable. I probably want to see some negative numbers, so like negative 10 for x and then 10 for y, because I want to figure out when it crosses the x-axis. All right, there I can see it. And notice that if you were to graph this differently, you would see 2 points of intersection because this is a quadratic. So it is going to cross the x-axis in 2 different locations, but I only care about where it's crossing over this interval. Okay, and then we're going to guess. Sure. All right, we get 6.3785. 6.3785. Okay, so at t equals 6.3785. Again, on the interval, there might be a second location where this function, in fact, there is a second location where this function is equal to 0, but I only care about over my given interval. So at t equals 3.785 minutes, the bird is flying at 21 feet per minute. Okay, that's when the average velocity is equal to the actual velocity.